we're live right now. I am going to do a quick review, of the stuff we've covered so far in section 2.1. And that's going to be by way of, so first we're going to calculate the derivative by using the definition. And then we're going to calculate we're going to look at a more conceptual problem that, I put a practice question on the test, I'm sorry, yeah, there will be one on the test as well that I put in the review section, review list of review problems. All right, so here's how it goes. The first thing that I want to point out here again, let's look at something like number 31. And that's going to be our first problem today. Number 31. Again, these sessions are also recorded, so I do invite you to look again, listen again to this lesson again. It's not a big deal, so you have basically 3 hours every week to kind of go back and sort of you don't have to watch the entire lesson, just the points where you feel like you don't have a perfect grip. So I want you to use these. I see there's some people watching the lessons, but I'm not sure how many of you. All right, so here's the problem. So this is going to be again. This is so today's questions will be slightly more challenging than the usual ones. So this is going to be number 31 from section section 2.1, we said, and that's going to be the following. So they give you this thing, f of x equals 3x squared minus 4x plus 1. And they say find f prime of a. Since you all were more or less either were here or watched the lesson online, I'm gonna assume that you already are aware of a discussion that happens here when we calculate f prime of a. We're gonna use the definition, and we're gonna say f prime of a equals the limit as x approaches a of f of x minus f of a divided by x minus a. By now, you must have memorized this because you used it a number of already a few times. So you've seen this for sure. All right, so now this is, well, this might be one of those few things in calculus that you actually need to memorize. But just remember, this is nothing but the slope of a secant line, and it slides towards the tangent line as x slides towards a. So this is equal to the limit as x approaches a of, and right now we're going to do our calculation. So we're going to put here f of x, and over here we're going to put f of a. So f of x in this quantity here will be just, I'm just going to copy the formula that's given here, this one here, folks. So this is f of x, this guy. All right, so I'm just going to copy that, and I'll put in here 3x squared minus 4x plus 1. And f of a, what about f of a? F of a is going to be, this thing where you replace x by a, right? Because that's what f of a is. So it will be 3a squared minus 4a plus 1. And that's divided by x minus a. And when you calculate this limit, you will get the following thing. So this is the limit as x goes to a. And over here we have, all right, so we have 3x squared minus 4x plus 1 and subtract. So let's put these together. So let's put 3x squared minus 3a squared. Yeah, these two, right? This one minus this one. Now remember that when we do a subtraction here, there's going to be minus 4x. Over here, there's nothing to worry about there. But then the next thing will be, so I'm going to collect the degree 1 part, so minus 4x, but look here, negative minus 4a is going to be positive 4a, so it's going to be plus 4a, and then we'll have 1 from here and minus 1 from here. 1 minus 1 is 0, so that goes away. So we really are left with just this part over here at the top after we simplify stuff. At the bottom, x minus a. And the way I'm writing it here is something that you can easily see how to factor things at the top. So my intention, folks, is to write this thing as, and I'm going to write without the limit again. I'll go to the limit at the end. 3 times the quantity x squared minus a squared. And then minus, and I'm going to subtract. So the thing is, it's minus 4 times, and then there's going to be x minus a. All right, so minus 4x plus 4a is minus 4 times x minus a, divided by x minus a. And that's going to be equal to, and if you factor here, you can see that this guy here, x squared minus a squared, does factor. So that's going to be 3 times x minus a times x plus a. Remember, we did this before. We had x squared minus 1, things like that. That's the exact same thing here. Minus 4 times the quantity, and then it's going to be x minus a divided by x minus a. And now we can actually start dividing up. So this really is, if you split this up, you could say 3 times x minus a times x plus a divided by x minus a minus 4 times x minus a divided by x minus a. So we just split this up here with the same common denominator, and we can simplify each of these guys. So there we go. So we simplify like that, and we really end up with 3 times the quantity x plus a minus 4. All right, so there's 3 times the x plus a from here, minus 4 from over here. And we're not done. Remember, we need the limit. So the limit, we need this. The limit is x goes to a of this guy. So of 3 times x plus a minus 4. And that's going to end up being, folks, that's going to end up being, you substitute a in the formula. Now, why could you not substitute earlier? Because earlier we had, x minus a would be 0 in the denominator. But over here we can. So we get 3 times a plus a is 2a. So that's going to be actually 6a. Over here, there's going to be 6a and minus 4. And that's going to be the result, our derivative. So this is going to be f prime of a. Now, those of you who have taken some calculus, like for instance, sort of high school calculus or something like that, may recognize that there is a formula there which says that when you do the derivative of 3x squared minus 4x plus 1, you get 6x over here minus 4 plus 0. So that's really this one here. But I did not do that. That's coming after we discuss this. We discuss this over here, and that's going to be something that we'll take care of 2 lessons later. All right, so this is the formula that they want us to figure out for the derivative. Now, let me give you the good news. So there's bad news and good news. The bad news is that this is always going to be a very laborious process. So it's never going to be very nice to work with this definition to calculate limits. The good news is that this is never going to be, or rarely ever going to be, the way one calculates derivatives. In fact, I don't think anybody in the right mind will start calculating derivatives with this procedure, in an engineering field. So folks, there are some formulas. So this is the good news. There are some formulas that we will get to as we move on. Move on. So we'll get to in a couple of lessons. and those formulas will be lifesavers. So basically derivatives will be a piece of cake. So you don't have to do these kind of things. Now, these kind of things though are required for us to teach here. I'm not sure how much of that will go on a test, so I'm gonna think about putting something slightly easier on a test. So not the kind of this level of this level of work is unnecessarily complicated, and really not many folks would use that in practice. Given that this is a class that not only teaches math majors, but also other majors like engineering majors, physics majors, biology majors, chemistry, and so on. All right, so there's a lot of things going on here, but I don't want to insist any further on this thing. I am going to tell you about something related, which more likely is that this is going to be something that I would put on a test. So this is going to be, folks. Any questions for me before we move on to the new problem? So okay, looks like no questions. Okay, so the next problem will be number 37, and this is a good problem because it really walks us through the key points without overburdening us with a lot of details. So 37 from 2.1, and this is why I like to put these kind of things on tests, something like this one. So the limit as h goes to 0 of square root of 9 plus h minus 3 divided by h. So this is the problem, and the question says this limit represents the derivative of some function at some number. Can you state such an f and a in this case? So we know that this is the derivative f prime of a for some f and for some a. What are those? So find f and a if you want. And well, so let's look here carefully what happens. So we have to remember the definition of a derivative. Now, which definition in this particular question? So we said there are two essentially equivalent definitions. So one of them says the limit f prime of a is the limit as x goes to a of f of x minus f of a divided by x minus a. But that's not the definition that I need because this one doesn't have the h. So there is one with h though, and this is the equivalent one, limit as h goes to 0 of, and there's going to be f of a plus h, remember, minus f of a divided by h. And I think it's fairly obvious that this would be the one I would need, not this one here. So in this particular context, because I recognize that, I have exactly that limit as h goes to 0, h goes to 0. I have the h in the denominator. So really, folks, all I need to do right now is to pay attention and take care of this thing in the numerator. So we want, first of all, we want f of a to be 3, but that doesn't, there's a lot of f's and a lot of a's that do that. However, the gimme here is this one, the presence of v square root. We want that to be here as well. So we want f of a plus h to be the square root of 9 plus h. All right, so now that pretty much will tell me what I want here. So what do I want my function f to be? I want my function f to be the square root function. And I want my number a here to be what? Well, this one that's missing here, so it would be, I want that to be 9. And then I can see that f of a plus h in this case will be indeed square root of 9 plus h. That's gonna be the thing here, folks. And this is quite important because the way the way things are set up here, we can also check that f of a, which is here, is equal to 3, because that's because the square root of 9 is equal to 3. So there we go. That's how we identify, folks. That's how we identify the answer to this problem. So we can say here, answer f is the if you want, f of x here is the square root of x, and a is the number 9. And that's going to be our glorious answer to this problem. So folks, I want you to be aware how these problems go. All right, so that's one of the things. Now, the next thing that I want to point out here is a similar problem where we're going to use the other formula, this one over here. So, so there is questions, folks? All right, so there is yet another problem that I wanted to discuss here, and that will be this one here. That's number 39. Again, these are practice problems, folks. You can, I put them on the list there. I put them on the list, so do study those, do review those at home. So how about this one? The limit as x approaches 2 of, and over here we have x to the 6th minus 64 divided by x minus 2. I want to write this as some sort of f prime of a. And again, if I were in a classroom, like a face-to-face classroom situation, I would, stop the recording. I mean, not stop the recording, but just pause, and I would let you try this particular problem, but maybe group works and stuff. But right now, given the current situation with the recording and such, I am just going to proceed to do this problem. However, I like to think that when you watch at home, if you go back and watch at home, you pause a video here, you do the problem on your own, you try the problem on your own, and then you look at the solution that I'm writing here. So in this case, again, remember that f prime of a, that's the one I want. All right, f prime of a is going to be the limit as x approaches a of f of x minus f of a divided by x minus a, and that is going to be equal to the limit as x approaches a of, and over here that should be look here at the limit, folks. Should be this one. So the limit as x approaches, I'm sorry, not a, it should be 2. As x approaches 2 of x to the 6th minus 64 divided by x minus 2. So by comparing the two formulas, I can see first of all that a has got to be 2. So I can choose a to be 2. That's very easy. And then I get the limit as x goes to 2, right? So I'm done with that part. I also see by identifying things, so then x minus a and x minus 2 identify themselves here at the bottom. I also identify f of x with this formula here, with f of x equals x to the 6th. And I only need to check that f of a, which is f of 2, is 64. Now, is f of 2 equal to 64? Oh, yes, it's 2 to the 6th, and that is indeed 64. So we satisfy everything by just, constructing the thing here, folks. So so the idea is to match things, to match the formula so that you can actually say, oh yeah, well, here we go. That's my function. My answer in this case is f of x equals x to the 6th, and a is equal to 2. So that is the answer, the one that I just boxed here at the bottom. All right, folks, I invite everybody to do the remaining problems. There's a few other problems here that are more or less in the same spirit as these two that we just discussed. But I am not going to do any more of those, so I leave those for you as practice questions at home. Please do let me know if you are having difficulties with those questions. All right, so now this lesson, I'm gonna move on to the next thing if there are no questions. So let me know if you have any questions, folks. With this, all right. Any questions here? Okay. All right. So the next question, the next section that I'm going to cover today is not something that I'm going to ask for on the second test, on the first test. So here's what it is. This is about calculating derivatives like we did in problem. Which problem was that? Problem one, I think today, the first problem, this one, 31 that we did here. So if you look at this problem here, this is really about, I give you a function and I give you a random number a, like this one here. So a is not specified as a concrete value, just a letter, right? So I give you that. Can you find me a formula for the derivative that would work at all a's? And well, 6a minus 4 is such a thing. So that's why what we did here is really an introductory part to an introduction to lesson 2.2, which looks at the derivative as a function. All right, so we get the derivative as a function, and this is something again. So it's just a review if you want. So remember that when we calculated the derivative at a number a here, we did this limit as x approaches a of f of x minus f of a over x minus a. And of course, this can be done at all points a of the domain. And if there is such a thing, if our function f has derivatives at all points a where it is defined, we say that f has a derivative. Now, this derivative can be thought of as a function that maps each number a to whatever value we get for the derivative or the slope of a tangent line at the graph on the graph above a. So this is a function, and this is called the derivative function. All right. And this derivative function, of course, can be calculated, and we will spend some time calculating such things. In fact, from now on, we will spend most of our time calculating general formulas for various derivatives. There is a very comprehensive set of examples in the book about doing derivatives with a definition. Again, I'm not going to insist on that. I'm going to ask a question on the test, well, a related question, but I'm not going to insist on, well, here, do the derivative this way with a definition, because as I said, the calculations are very laborious sometimes and unpleasant. And we're going to discuss about a graphical interpretation, if you want, of these derivatives. And if you look in the book, you will see a bunch of numerical examples. And numerical examples, anybody can, I'm pretty sure everybody can calculate limits by now. So I'm not worried much about those, but there's some examples with graphs that actually are a bit challenging, and I want to do a bunch of those so that you can see that you can, even though you don't know anything about the function itself other than a graph, you can still sort of figure out the shape of a derivative, how big the derivative is. In fact, that's what we're going to do here. So let me actually explain you how to do such an example. And I am going to do something like, I'm going to go start with problem 3. And problem 3 is slightly different than what I do here, part A. It says here you have a function, and it's not given in terms of a formula, so we don't have anything like that. So with this, it's useless, this definition here. We don't have anything like that. Instead, we have a graph that goes something like that. And this is our function y equals f of x. And the question is, can you say something about the derivative of this function? So if you were to graph y equals f prime of x, what would the graph of that look like, the derivative? And this is a really good question. So what would the graph of a derivative look like? Oops, okay, I can move this up. All right, so we are going to address this question over here. All right, so when we graph the derivative, folks, remember that, so this is what I'm gonna graph the derivative. Remember that every time I'm looking here, and actually let me redo this. I'm gonna do on a new page, so I have a clean page here, folks. You don't have to erase anything. I'm just gonna do some straight lines. Let's make a nice picture because it's really worth having a nice picture here. There we go, something like that. And let's do a comparison here. So the derivative, okay, another picture here. All right. So there we go. So let's have some nice drawings here. So this is y equals f of x. This here is going to be y equals f prime of x. All right. So let's get to work on that. All right. So we said that our f was again in the book. All right. So it goes like this. And the next one goes, well, how does the graph of f prime go? So here's how they go. I'm looking at f prime over here, and I'm looking for the slope of a tangent line because that tells me the whole story about f prime. That's the slope of a tangent line, right? That's what f prime is. And if I look here carefully, I can see that that the slope of a tangent line is negative if I'm a little further right with the x. If x is down here, towards the left on the side of the x-axis, the derivative is going down is negative, right? Negative, very negative. So the derivative would be someplace here if I were to plot it on this graph because it's x is negative and the value of a derivative, the slope of a tangent line is negative, right, folks? So I'm going to plot a point here corresponding to the derivative at this point. And it's negative over here too when it crosses the x-axis, but it looks like it's not as sharp going down as it was above there. So maybe I'm gonna say, well, maybe it's somewhere here. But look at the interesting thing. Or let me plot it maybe a little to the left, like something like that. So let's say. But look at what happens here as we go down and down and down with the derivative. Well, that looks like the slope is, even though negative, is still, well, it's kind of increasing and it gets close to zero because look here, folks, at the bottom here, over here, the derivative, the slope of a tangent line is zero. It's a tangent line is horizontal. So really, at some point here, which corresponds to this one here, the derivative becomes zero. And as we go closer and closer to the origin with a derivative, the slope of a tangent line now becomes positive, and it gets more and more positive. And it looks like over here it has some sort of maximum over here where the x-axis is. So remember that even though I'm at zero here, the slope of a tangent line is not zero, is something like that, is maybe 1 or something. So that's why I get this point here. So this is 0, 1, that corresponds to the value of a derivative. And then as I go past this point, past 0 on this other side, the derivative is still positive, but it seems to be decreasing, and all the way up to here where it's 0 again, the slope of a tangent line is horizontal. So, so I'm going to say, well, maybe my derivative goes like this. And over there, it crosses the x-axis. So, so this point corresponds to this one here. And over here, it crosses the x-axis and it goes down. So it goes down, 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 down. It becomes more and more negative. So, so this is what the graph of a derivative looks like when we calculate the derivative of this one function over here. And in the book, so this was part A, and in the book they say match what's given here. This is given with blue colors, match with the one in red. So the one in red that's matching here is the one at number 2, example number 2 in the book. So that's A is matching number 2. That's how you do this particular problem. All right, I'm going to do another example from here. So again, this is all about using graphical, it's the giant graphics exercise in graphing, right? So this is the part B here. We get another, let's do a nice picture here again. So let's go over here more this way and this way. There we go. And we got the graph which goes this way. All right, and then it goes down like this. Oops. Something like that. And then from here it goes, just stay there. All right, it goes up like that. There we go. So that's the graph in part B. And then he says here, do the derivative of that, represent the derivative on this real number line. All right, so let's do that. Let's represent the derivative. And here we go again. So so this is my function. This is going to be f prime here. This is f over here. So different situations, different scenarios. Now the derivative for any point here on the x-axis to the left of this over here on this side. All right, any point here will be, and maybe I should do with red. So let's do with red here. Just there we go. So if you look at the derivative is a function itself. This is a linear function, right? So it stays constant. The slope of a tangent line stays constant. And if I represent it here, that will represent some points going like this at some constant height, maybe 1, all the way up to some point here where there is a corner. And over here, I don't really have a derivative because as I go from the left, my slope is like that. But when I go from the right, my slope will be the other way around. So that's okay. I'm going to put that point, maybe, like a circle here, meaning that the derivative might not exist there. It doesn't, but didn't discuss about that. And then as you go down the other side, again, constant, but a negative value for the slope of a tangent line. So, so I have a constant value, but a negative value, right? So the points for the derivative are something like these. There we go. And finally, I reach this other corner here, which corresponds to some, I don't know, some value of x. And over here, that will give me another, I think, another one of opening of these, because as I turn around here, I get another value of a derivative, which is positive as I get past that point, and it's positive and constant all the way to infinity from here. So really, the derivative will be a bunch of, when you plot it, a bunch of constant points at height, whatever the slope of that line is. And if you look here, that's fairly obvious what the matching graph is. If I look here in the book, you will see that that matches the example at 4. All right, folks. Any questions here? I'm going to do one more of these and I'll be done. Okay, so let's do, all right. So let's do another example from this problem. That's going to be problem 3. Let's do problem 3C of section 2.2. And that's going to be the following. So let me draw again. Let me draw a nice picture, because a nice picture will help tremendously in these problems. There we go. And we have now, I have to draw the rest of the graph by hand, but I can sort of see that it's, an upside down bell, if you want, something like this, folks. This is the graph of, again, this is the graph of f of x. The x-axis going this way and the y-axis going that way. And let me actually do a similar thing over here. Not bad. Let's do a straight line. There we go. Come on. All right. So we got that. Again, the same situation over there. Put this one too much to the left, to the right. So I'm going to put it a little more in the center. Okay, there we go. Something like that. And again, that's the x-axis, and that's the y-axis. And this is y equals f prime of x. Okay, so that is the derivative, and this is going to be something that we have to figure out. So let's figure it out. All right, now what happens over here when I go to the leftmost? I'm going to change the colors here just to be more visible. So the derivative is fairly close to being 0 or horizontal, the slope of a tangent line, right? So basically it's close to 0, and then it goes slowly goes down, but not too much, because as I get to some place somewhere here, you can see that it starts flattening out again, and it really gets closer to 0. So it goes down a little bit, the derivative, like this, but then it kind of turns around like that. And I'm going to delete these things because it wasn't a nice picture. I'm going to make them a nice picture now. All right, and that's going to be, so it goes slowly like that, and then goes kind of like that. It becomes 0. It grows a little bit, it kind of grows a little bit like that, but then it flattens out somewhere here, and then it goes down again. Still positive, but very close to 0. So look at my derivative. This is the graph of a derivative. Again, I'm looking at the slopes of the tangent lines, and I can see that, the idea is that a line going this way has positive slope, and a line going down has negative slope. That's the whole thing here. So that's why I'm plotting these points above and below the x-axis, and the sharper the line is, the higher the slope is, right? The sharper the line is down, the lower the slope in the negative direction. So this is going to be the answer to this particular problem, and that is part, let's see, part 1 in your text. And it remains for you to match by following the exact same example. Now we matched 3 of the 4, right? So the 4th one would be the remaining. All right, so it remains for you to match, and you will see that part D of your question matches, of course, the remaining one, which will be number 3. So please match that. Now this is the stuff that I have prepared for today. I don't want to push any further, so we are going to do a couple more examples from this lesson as we meet after the test. So that will be Monday, and then we're gonna focus on differentiation formula. So maybe yet another example like this Monday, and then we'll do the important things, which will be derivatives that really are useful for us to calculate general derivatives. All right, folks. So this turned out to be a shorter lesson in a way. I am going to stop the recording here.